Pluto is a distant and clandestine, more modest planet that was once a part of our nearby planetary group. However, ongoing disturbing announcements by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight with a dazzling revelation. They suggested that this chilly world is on a potential collision course with Neptune. But how could this actually work, and what may be the results of such a colossal event? Are we seeing a charming cosmic idiosyncrasy, or is there something more to this approaching endless accident? Join us as we examine the likely results of a Pluto-Neptune impact. Pluto, a previous planet that was minimized to a dwarf planet, remains a subject of interest and study in the cosmic community. As indicated by recent forecasts by leading specialists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a possible dangerous collision between these two planets, which could pose a tremendous danger to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It requires a dazzling 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even finished one full revolution. However, the interest doesn't stop there. Pluto's orbit is marked by its exceptionally elliptical shape, wandering extensively from the nearly round orbits of the major planets. What makes Pluto's orbit even more remarkable is its inclination, determined at 17 degrees to the ecliptic plane. The way Pluto follows its path is much more extreme compared to other planets. This inclination and eccentricity add layers of complexity to its orbital design. One of the most intriguing parts of Pluto's orbit is its crossing point with Neptune's. For around 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, testing what we could expect from their positions in the solar system. This prompts the regular question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to figure out its unique path. Unlike other planets, whose orbits lie relatively close to the ecliptic plane, Pluto's orbit sticks out with its steep inclination and elliptical shape. The mystery grew with the realization that Pluto's orbit does, in fact, cross Neptune's. The stability of Pluto's orbit amid these intricacies is evidence of the complexities of celestial mechanics. The three-body problem in space involves determining how three objects in space, like Pluto, Neptune, and the Sun, move and affect each other with their gravity. It's like trying to predict where they will go based on where they started and how they pull on one another. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity all work together in a complex way. The terms asynchronous libration, orbital precession, and the VZK oscillation are important for this puzzle. According to astrophysicists, what keeps all planets in their orbits is asynchronous libration with respect to Pluto and Neptune. This term means that whenever Pluto crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune. This spatial separation is crucial in keeping their orbits from converging. Orbital precession, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, providing an additional layer of protection from potential impacts. Another critical aspect in this situation is the VZK oscillation, named after three researchers, Zell and Kai, who studied how objects move in space. It involves the way three space objects, like Pluto, Neptune, and the Sun, pull on each other with their gravity. This pulling affects how they move. In Pluto's case, the VZK oscillation helps us understand why its orbit near the Sun is so unusual. Despite Pluto's path seeming erratic, this oscillation helps keep it moving smoothly over long periods. The VZK oscillation shows that even though things in space appear chaotic and unpredictable, some patterns and rules keep everything in order. These factors help keep Pluto's orbit stable, ensuring that it doesn't collide with Neptune or stray off course. This three-body problem is crucial to understanding how these orbits change due to the way space objects pull on each other. Studying this helps us learn more about Pluto, our nearby solar system, and even distant worlds and their stars. Numerical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is actually volatile, with minor deviations in initial conditions leading to significant differences over thousands of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the disruption under control. Later programmatic studies have helped us understand how the giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This relationship helps keep Pluto's orbit stable. However, Neptune isn't the only one at work. Jupiter's gravity also plays a huge role in stabilizing Pluto's orbit. Saturn also contributes. These studies show that Jupiter's immense gravity is strong enough to ensure that Pluto stays on a steady path for a long time, even millions of years. So it's as if Neptune, Jupiter, and Saturn are all working together to ensure Pluto continues to move safely through space without running into trouble. These phenomena are essential for maintaining order and stability in space. Without these mechanisms, the solar system as we know it would be a much more turbulent place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction with other celestial bodies. For Pluto, particularly with discussions about it potentially slamming into Neptune in the future, understanding its orbit is crucial. This provides a clearer picture of the dynamic nature of the solar system. The case of Pluto shows how even the most seemingly unstable orbits can reach a state of equilibrium through the complex interaction of gravitational forces and orbital mechanics. It also demonstrates the importance of continuous observation and study of these phenomena to better grasp our place in the universe. Exploring the depths of space often leads us to confront the odd nature of celestial bodies, and Pluto's orbit is a perfect representation of the unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in Pluto's case. This means that even slight changes in the dwarf planet's position or speed can significantly alter its long-term orbit. Using programmatic simulations has been immensely helpful for researchers in figuring out how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other space objects, like Neptune, pull on each other. By tweaking small details in the simulations, space scientists can see how even tiny changes can have a big effect on where Pluto ends up. In the late 1980s, these simulations showed something interesting about Pluto's orbit. Even though it has elements like asynchronous libration and orbital precession to keep it stable, its orbit can still be erratic and whimsical. If you start with just a small difference in where Pluto is or how fast it's moving, its orbit could end up looking completely different after a few years. Yet even with this chaos, Pluto's orbit remains stable over really long stretches of time, like billions of years. This truly means that Pluto's journey around the Sun has a kind of order to it, even though it seems turbulent at first. Predicting celestial events, especially when they involve violent orbits like Pluto's, is a huge challenge. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While numerical models provide powerful tools for understanding and predicting the future paths of celestial bodies, they also highlight the limits of our predictive abilities. These models depend heavily on the accuracy of initial conditions, and any small error or distortion can lead to vastly different results, making precise forecasts a daunting task. Moreover, the turbulent nature of planetary orbits, like Pluto's, reminds us of the ever-changing and dynamic nature of the universe. While we've made huge strides in understanding space, Pluto's case reminds us how much our knowledge of the universe still remains limited. Understanding the gravitational effects of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can significantly affect the stability and direction of other bodies within the system. So why are leading astrophysicists recently raising concerns about a potential collision between Pluto and Neptune, despite all these complicated forces trying to prevent such an event from happening? Neil deGrasse Tyson, a prominent astrophysicist and a major figure in popularizing cosmology, offers a unique perspective on the mysteries of our solar system, particularly the fascinating case of Pluto. Tyson, known for his role in renaming Pluto from a planet to a dwarf planet, offers insightful analysis on the evolving nature of celestial mechanics and the public's interest in the neglected realms of space. Tyson's position on Pluto's renaming is based on the ever-growing knowledge of our solar system. He views the renaming not as a diminishment but as an important adjustment to our expanding understanding of the many bodies orbiting our sun. Tyson's approach to celestial mechanics is one of continual learning and transformation. He sees the complexities of orbits like Pluto's as a sign of how much there is still to discover in space. The intrigue of these questions is what keeps the study of space so exciting. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune paint a different picture. His concerns about the future of Pluto's orbits suggest that we may still have many more secrets to uncover. Will Pluto crash into Neptune? Or is this just another moment of confusion in the constantly changing world of space? Only time and further investigation will tell. For now, we are left with a deeper curiosity about how little we still know about our own solar system. We continue to study these celestial phenomena with hopes of uncovering more of the secrets that lie beyond. The possibility of a Pluto-Neptune impact raises just another question about the mysterious and intriguing universe in which we exist. The potential for a crash between Pluto and Neptune raises fascinating issues about the dynamics of the solar system, as it challenges conventional understanding of planetary stability. The idea that two celestial bodies with such vastly different characteristics could collide is both disturbing and intriguing, especially considering the current relative strength of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is itself a gas giant with a strong gravitational field, the implications of such a collision would be significant for our understanding of gravitational interactions and the evolution of the solar system. To understand the dynamic of a potential impact, one must first consider the structure and properties of the two planets. Pluto, despite being a dwarf planet, contains a variety of elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere made mainly of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a giant gas planet, is made mostly of hydrogen, helium, and other lighter elements, with a deep, dense atmosphere. A collision between such disparate bodies would dramatically affect their structure and behavior, possibly creating an event that would be visible across vast distances. What makes this hypothetical impact especially fascinating is the influence of other planets and bodies in the solar system. While Neptune's gravity plays a dominant role in keeping Pluto's orbit stable, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another key element. Jupiter's immense mass, strong gravitational field, and gravitational pull provide a stabilizing effect on Pluto's orbit, preventing it from wandering too far into Neptune's territory. Additionally, Saturn's gravitational influence further complicates the dynamics of the outer solar system, making it less likely that a catastrophic event will occur between Pluto and Neptune. Despite the apparent risks, ongoing research has also shown that the relationship between Pluto and Neptune is not as simple as a straightforward collision course. The gravitational resonance between the two planets, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a kind of cosmic lock that prevents them from coming into direct contact. This resonance is a key reason why Pluto and Neptune's orbits, while intersecting in the vast expanse of space, have never resulted in a collision. The orbital mechanics of these bodies are aligned in such a way that the potential for conflict is minimized. To further understand the intricacies of Pluto and Neptune's relationship, it's important to consider how the behavior of their orbits aligns over long periods of time. Even though Pluto's orbit crosses Neptune's, the two bodies never actually collide due to their gravitational resonance, which ensures they are safely locked in a stable pattern. This remarkable cosmic dance is a result of both planets' orbital periods being in a 3:2 resonance. Essentially, for every 2 orbits Pluto makes around the Sun, Neptune completes 3. This synchronization ensures that even though their paths may cross in space, Pluto and Neptune are always far enough apart at any given point in their orbits to prevent a collision. This resonance is a beautiful example of how the delicate balance of forces within the solar system works to maintain stability. Without this kind of orbital harmony, Pluto would be at risk of drifting into a more chaotic path, potentially interacting with Neptune in a way that could disrupt the balance of the outer solar system. The gravitational interactions between planets, especially those as massive as Neptune, Jupiter, and Saturn, also act as protective forces, keeping Pluto in a relatively secure orbit despite its unusual characteristics. In addition to the gravitational forces at play, the overall structure of the solar system also plays a role in minimizing the likelihood of catastrophic events. The outer planets, with their immense gravitational fields, act like sentinels, constantly shaping and reshaping the orbits of bodies like Pluto. This constant interaction keeps the solar system from devolving into chaos, with planets and smaller objects following predictable, though sometimes eccentric, paths. Despite these stabilizing forces, there remains an element of unpredictability in the long-term evolution of the solar system. As we continue to study the behavior of distant bodies like Pluto, we are reminded of how much we still have to learn about the dynamic, ever-changing nature of our universe. While a collision between Pluto and Neptune remains highly unlikely due to their orbital resonance and the gravitational effects of other planets, it still serves as a reminder of the complex and fascinating forces at play in our solar system. The possibility of such an event challenges our understanding and keeps us eager to explore the mysteries of space.